Now, we had before angular momentum of a point particle moving in some goofy direction. And if you recall, we said it's the moment of inertia times the angular velocity. Well, the moment of inertia would be the mass times the distance squared, and then I multiply by omega. So let me factor out 1r, that leaves mr omega. R omega is just v, the component of the velocity that is actually perpendicular to r, that's making it go around. So I take the component of v that's perpendicular, that's here, so r times, and then that looks like the perpendicular component of momentum, and this seems to be the recipe for getting the magnitude of a cross product. And so it seems reasonable that the angular momentum should be r cross p. So that's the angular momentum, the vector angular momentum for a point particle that's moving with some momentum p. Okay, and once again, r is the vector that goes from whatever is the origin that you've picked for calculating angular momentum out to the particle. Yes, sir?
Does that only work for point particles or rigid body?
Right, so then he's wondering, does that only work for point particles? And the answer is yes. And so if I have an extended body, what am I going to do? Yeah, so I would have L is the sum of r sub I cross p sub I. Yeah, so I have to use the position vector that's appropriate for each little bit of mass. So once upon a time, somebody asked me the question about, well, wait a second. Once the dumbbell is dropped, it's not moving around in a circle anymore, so doesn't its angular momentum instantly drop to zero? And I tried to argue that no, it doesn't, and it's still going around in a sense. Well, with this definition of angular momentum, r cross p, we can see that the perpendicular component of the distance between the line of propagation here is just b, this distance there, which is often called the impact parameter for one particle sailing by some center. And no matter where that particle is along the dotted line, it has the same r perpendicular, which is equal to b. And so let's see, did I get it right in terms of the direction? R cross p, is it right? Is it z, or is it minus z, or is it something else? Out of the page? Okay, so once again, r crossed into v, and the right thumb points out of the page. So that's in agreement with z. Okay, so that was easier than having to do fancy differentiation that we had to do before. So it's still true that a particle moving in a straight line at constant velocity in general has angular momentum. How do you get rid of that angular momentum? What would be a trivial way of saying that it doesn't? Yeah, stick the point, the reference point on that line somewhere, and then you'd get rid of it. Okay, what is the dynamical equation that we've been working with for rotational motion? Torque causes a change in angular momentum.